Okay, thanks very much. So I'll be showing you a look at trying to do feedback modeling, and there's two different parts to this talk. The first part will be a summary of some work that was done as part of an international collaboration. That's all my co-authors in italics there, and then I'll be getting into some more recent work that we've been doing at high resolution just within Environment Canada. So the question that I'm trying to address here is, to what extent do human activities that result in emissions and or chemical formation of particulate matter change the weather? And the tool that we're using to do that are fully coupled air pollution weather forecast models. That is, you have both the air pollution and the weather components within a single code that makes them coupled, and more importantly, they can interact, which is the fully coupled part. I'm sure most people here in the audience know the definitions of aerosol direct and indirect effect, and those are the two things that we're trying to incorporate in these models. Basically, how much the particles will scatter light and re-emit it as infrared sometimes, and for the particle formation for clouds, cloud condensation, nuclei formation. Now, most weather forecast models will have parameterizations for this, but the point is, when you actually start trying to simulate what's happening in the real atmosphere, when you're talking about particles that have been formed as a result of human activities, you get local changes. The particles can change the weather, but the weather can change the particles and vice versa. And you can go through a sequence of events such as I've shown here, where eventually you can get to a point where you're saying particles affect the weather, affect the particles, affect the weather, and you get feedbacks. How do those things affect things in terms of your forecasts for both weather and air quality? Well, what we did within the context of both of these studies is try doing feedback and no feedback runs. And the basic idea here is you've got a model that can already do the interactions between the weather and the air quality, and you break that link and do a no feedback run. And sometimes you're using a model that, in that case, that has a parameterization instead of the actual detailed chemistry. And then you also compare that to a feedback run. So you do parallel forecasts, and you see how this changes the system. So for ACME 2, that stands for the Air Quality Model Evaluation International Initiative, and it's phase 2 of that. And this involved 15 research institutes, and we were running these fully coupled models for, in some cases, 4 years' worth of output. You're doing successive 48-hour forecasts in both North America and Europe. And we're at the point now, most of the papers have been accepted in atmospheric environment, and we're working on the preface for it. So I'm going to talk about 2 of those in particular and get into some current work. Some of the things that we found, though, by doing these sorts of simulations. First of all, we did see that there's the potential, at least, to improve the forecasts of both weather and air pollution by including the feedbacks into the model. They're not random effects. It's not a chaotic difference between them. They're systematic. They vary in time and space, and more importantly, they vary where you see the emissions are the highest and where the chemistry is the greatest. And they're strongest close to large sources of pollution. I was really happy to see the first speaker's talk with the power plant, because that's exactly the kind of thing that we're seeing, but on a larger scale over larger areas. The models which accurately include these things will actually do a better job. So here's an example from ACME 2. These are for the year 2010, and they're showing all of the surface temperature monitoring stations in North America and in Europe that were part of the study. And what's specifically being shown here is the difference in the mean bias of temperature between observations and the model runs, but it's the difference between a feedback run and a no feedback run. And so it's the absolute value of the mean bias. Basically, the closer you are to zero bias, the better the simulation. Anything that's a blue color, sort of bluish to greenish in these, are cases where the feedback run has improved the temperature forecast in terms of the mean bias. So you can see over most of North America, you do get those sorts of improvements, especially in the western United States, lesser extent in the east. It actually got a little bit worse for Alberta, Saskatchewan, and Canada. And then for Europe, there were improvements in temperature pretty much over the whole area. These are 2 different kinds of models here. GEM-MAC had both indirect and direct effects, whereas the WRF-Chem simulation in this particular case had direct effect only. And the magnitude of the change in the temperature has changed as well. Minus 0.4 to plus 0.4, minus 0.08 to plus 0.08. And that's one thing that was consistent across all of the simulations. The indirect effect seems to be the dominant of the 2. This is another example, looking just now for a shorter time period within the runs that were done in Europe from July 25th to August 19th. And the reason why we focused on that time period is because there were some very large forest fires taking place in Russia at the time, and those were included in our emissions data. And this is the effect of those on the feedback, or on the forecasts of surface downward shortwave radiation. So these are deltas. These are changes in shortwave radiation. The area of the forest fire stands out pretty strongly. Minus 80 watts per meter squared. That's the change in the downward shortwave resulting from the fires. That's the change in surface temperature. It gets down to minus 0.8 degrees Celsius over quite a large area. So where we're going with this in Environment Canada now, we've got a nested setup where we're going from a continental domain, it's 10 kilometer resolution, down to a local 2.5 kilometer resolution over Alberta and Saskatchewan. And we're doing a shorter period run, basically because the CPU time to do it for a year would be immense. But the reason why we've chosen this 1 month period is we've also got some measurement data from monitoring intensive that was going on in the Canadian oil sands at the time. This is with the GEM-MAC model only now, and we're comparing the highest model resolution results to observations. We've just done the air quality comparison so far, not the weather side though. Just to give you a feeling as to what kind of things are changed in the model between, I call it original revised here, but this on the left is the same as no feedback and feedback. The standard weather forecast version of GEM-MAC, or the air quality forecast version of GEM-MAC, has specified functions of aerosol optical depth, single scattering albedo, and asymmetry factor for the direct effect. And in feedback run, that's been replaced with a ME algorithm lookup table that's basically taking the aerosols that are generated by the model and saying this is what the radiative properties would be. And then for the indirect effect, there's a Milgrant-Yau double moment scheme. There's a parameterization for cloud condensation nuclei, just as a function of supersaturation that it uses. And that's been replaced with Abdul-Razak-Gan scheme, which is by aerosol size and speciation. So the air quality part gets into the model that way. And then you complete the feedback loop by having the cloud droplets from microphysics going to process the gases. So you do a set of overlapping runs at successive higher resolution. We start off with a backbone run, that's the lowest resolution, and then we're doing feedback and no feedback simulations going down to 2.5 kilometers off of that with enough spin-up time for the clouds to basically settle down. And then we compare those runs to surface observations. So that's our three nesting setup. The outer domain is the continental one, then we have a 10 kilometer domain and then a 2.5, and it's about 650 by 550 grid squares at 2.5 kilometer. So when you look at some of the results of those simulations, part of the reason why aside from the fact that I have this set up for the oil sands and for Alberta and Saskatchewan, this is sort of Texas North, so we know that we have quite a lot of emissions going on here. You look at the feedback and the no feedback runs just by themselves, they look pretty similar. And then if you do a difference plot over that time period, however, over a large part of the area, you get the blue colors, 0 to minus 0.65. You get decreases in temperature, some smaller areas where there's increases. So these are shorter than a year's worth. We did actually see some impacts. That's the turbulent kinetic energy. Southern part of the domain, there was decrease, but larger increases in the north. And this seems to have affected the dispersion of the pollutants. So if you start looking at things like the particulate matter, what's the impact of these changes on the PM 2.5? That's 3 micrograms per meter cubed increase due to simply including feedbacks into the model and downwind. So these are getting to be quite significant in terms of the air quality side of things. You can blow up individual source areas. So this is the Canadian oil sands, and what was the impact of including feedbacks? There's changes where the PM 2.5 is on average has decreased versus increased, and that's because the plume directions are changing on average over that time period. If you look at ozone, the lowest end of the scale is minus 5. Now, the standard version, the no feedback version of the model, actually has a positive ozone bias. So things that are decreasing are pushing it in the right direction. And you can blow up individual areas. Again, you see quite large decreases close to some of the big sources. NO2, another example. This is getting closer to the emissions that are creating the ozone. And again, close to the facilities in the oil sands area, you get a larger amount of changes. Now, there's about 4 or 5 major plants here altogether. So these are, thinking about the first speaker's talk, you've got a whole conglomeration of sources of SO2 and particulate in that area, and you get these changes. You get other downwind effects if you're concerned about acid deposition, for example. The amount of SO2 that's been deposited downwind has increased with the feedback version of the model. And you get some quite striking differences in where SO2 is being deposited. And what's happening here is the feedback and the no feedback model are putting the plumes in different places. So the wind directions have changed, and the amount of SO2 that's deposited close to the sources have changed. And that's why you have these sort of bimodal, almost flower-like patterns around some of the big sources. Cloud liquid water, zoom in over the oil sands area itself, and there is actually a local doubling of the cloud liquid water close to the source. But I've added the word significant here because, of course, we do have these changes in the model, but you can get perturbations chaotically as well. So this is something we need to follow up on. But over the larger scale, we do see some significant changes in the precipitation. Specific humidity at the surface dropped when we included the feedbacks in the area. So that's roughly the usual downwind direction. So you get changes in the specific humidity. It's about 2% of the no feedback case. So in terms of evaluation, what we've done so far for the high resolution stuff is just looked at some of the chemicals, because we have a surface monitoring network for that as well as the meteorology. And I've got different statistical measures here, but I've colored them green or red for which one did better. So the no feedback is the base case, the feedback is one called feedback. And for some of them, the NO2 and the ozone, for example, you actually get improvements. PM 2.5 got a bit worse. This is over the whole domain. When we zoomed in on the oil sands, where we've got actually better emissions data and also a number of stations that are close by, that seemed to actually improve some of the PM 2.5 as well. But the ozone and the NO2 are across the board a lot better now. And these are sometimes fairly significant differences in the ozone performance of the model. So the model is actually working better when we include the feedbacks. Another way of trying to look at the evaluation is just, these are histogram differences at observation stations. So just it would be better if I did these as bar plots, but it's the feedback histogram minus the no feedback histogram. And what I was looking for in this was any sort of coherent shifts. And you can see one here in the ozone, for example, where the number of times you get ozone that's between 30 to 60 parts per billion has decreased with the feedbacks, and then the lower concentration values have increased. The NO2 is a bit up and down all over the place. There's a lot more active chemistry going on with that. And the PM 2.5, there's a large number of times when there's high values that have now become relatively lower values. If you zoom in on the oil sands area, it's harder to pick out the differences from the noise, though, because it's about 6 stations and closer to the source regions as well. But you still get a change. So for the high resolution stuff, some preliminary conclusions from it. Well, like the ACME case, we see that the air pollution can affect the weather and vice versa. It's a small effect, and I should mention for the ACME runs, when we were looking at the different models that have been configured this way, we could see that we were consistently getting an improvement in the forecasts for a number of the meteorological parameters and the air quality parameters. But the difference was that when you looked between the different models, you got a bigger impact. So it's not like this is something that's going to be a silver bullet that will improve the model more than other parameterizations, but it still does have an impact. We got improvements for ozone and NO2. It got worse for PM 2.5, and the effect's more noticeable when you get closer to the region of higher emissions. So where it goes, that special issue should be out within the next month or so, touch wood, and we're doing some more of these high resolution runs, and we're going to go on to the surface meteorology and probably do some comparisons with just direct effect only, and try it out for Pan Am Games in Toronto, which is coming up. So thank you for your interest.
Well, I don't know what happened to the lights, but we have time for a few questions. I have a quick question. I think the feedbacks to aerosols and other gases are interesting. There's a well-known central U.S. warm season bias in central U.S. and Canada. Do these feedbacks of aerosols help improve that bias? I mean, it's typically a 2 to 6 degrees Celsius bias. And I at least in the numbers I thought I saw,